All right, hello and welcome. Today we're going to dive into one of the most powerful tools in all of engineering and math, the Laplace Transform. We're going to see some really tough calculus problems get completely tamed.
So let me just start by asking you a question. What if you could take a differential equation that looks like an absolute nightmare and with one single clever move, turn it into a simple algebra problem? You know, the kind you could have solved back in high school? Well, believe it or not, that is exactly what the Laplace Transform promises to do.
Now, to really appreciate just how cool this is, we first have to understand the problem. See, we usually look at how things change over time. That's what we call the time domain. And in this world, some equations that describe real-world systems are just incredibly hard to solve with the tools we normally use.
And look, don't get me wrong, our standard calculus methods are great for certain types of problems, especially ones with nice, smooth, predictable functions. But let's be real, the world isn't always so neat and tidy, right?
So what happens when your input isn't smooth? What if it's a function that's defined in different pieces? Or what about a sudden sharp jolt, like the exact moment you flip a switch in an electrical circuit? For these kinds of real-world problems, our usual methods, they kind of fall apart. We need something more powerful.
And that is where our hero enters the story. Think of the Laplace Transform like a magical portal. It lets us take a really difficult problem from our world and transport it to a brand new world where everything is just so much simpler.
So, how does this portal actually work? Well, this formula you see here, that's the engine. We take our function, which depends on time, f of t, and we feed it into this special integral. Now, don't get bogged down by the formula itself. Just think of it as a conversion machine. It takes our time-based function, processes it, and spits out a brand new one, f of s, that lives in a totally different world, the frequency domain. It's kind of like if the time domain is watching one person play an instrument, the frequency domain is like seeing the sheet music for the entire orchestra. It's just a different and often more useful way of looking at the exact same thing.
And this right here, this chart really sums up the whole strategy. We leave the t domain, where calculus can be a real headache, and we travel to the s domain, where those same problems turn into basic algebra. And why does that happen? Because the transform is specifically built to turn calculus operations, like taking a derivative, into simple multiplication. We solve the easy problem over there, and then we just travel back.
Okay, let's actually try this out. Let's send the simplest function we can think of. F of t equals 1, right through our portal. So we set up the integral, we solve it, and then when we evaluate the result, something really cool happens.
And there it is. The constant function 1 in our time domain becomes the function 1 over s in the frequency domain. It has a completely new identity in this new world. That is our first successful trip through the portal.
So, we've sent a simple function through the portal. Awesome. But now it's time for the main event, the magic trick that makes this whole journey totally worth it.
Okay, listen, if you take away only one thing from this explainer, let it be this. The transform takes those tricky operations, like derivatives and integrals, the very heart of calculus, and it converts them into simple multiplication and division. All of that hard calculus just, poof, vanishes. So this gives us this beautiful, simple, three-step master plan. Step 1, you transform the entire ugly differential equation into the s domain. Step 2, you just use basic algebra to solve for the answer, which we'll call y of s. And step 3, you bring that answer back home.
All right, so we've solved our problem over in the s domain. We have our answer, y of s. But now what? How do we get it back to our world so we can see what the actual solution y of t really looks like?
Well, we need a portal to come back, right? And that's exactly what the inverse Laplace transform is. It's the operation, written as L to the minus 1, that just reverses the whole process. It takes our solution f of s and brings it right back to the function f of t that we actually care about.
And honestly, here's the best part. While the journey to the S domain required solving that integral, the journey back is usually way easier. We don't need another complicated formula, we just read the map in reverse. You see, engineers and mathematicians have already created these huge tables of common transforms, so we can just look up our answer, like 1 over s minus a, and find the original function it came from. It's kind of like looking up the answer in the back of the book.
And you might be wondering, well, what if my solution is super complicated and it's not in the table? No problem. There's a powerful algebraic trick called partial fraction decomposition that lets us break down that complicated function into a bunch of simpler little pieces that we can find in our table. So let's just put this all together. This entire process, this whole journey, gives us a systematic way to unlock solutions to problems that before this, might have seemed completely out of reach. So let's just recap our journey real quick. We started with these tough differential equations in the world of time. We used the Laplace transform as our portal to get to the world of frequency. And that was the magic step that turned hard calculus into simple algebra. After solving it there, we used the inverse transform to bring our solution back home, giving us a real-world answer that we can actually use.
And that kind of leaves us with this really fascinating thought. This whole idea of transforming a problem into a different domain just to make it simpler is an incredibly powerful concept. It really makes you wonder, now that we know we can do this for differential equations, what other seemingly impossible problems are just sitting out there waiting for the right transformation to make them simple?